Hi everyone, today we're going to be going over entropy and enthalpy and Gibbs free energy from Module 11. So just as a refresher, we're going to be going over some basic definitions, starting off with energy. Energy, of course, is a thermodynamic property and it is the ability to do work. Entropy is the measure of molecular randomness or disorder and it's a state function, and we'll touch more upon entropy in the following slides. Enthalpy is a thermodynamic property of a system, and it is the sum of the internal energy with the product of pressure and volume of a system, and delta H is equal to the change in energy. Gibbs energy combines entropy and enthalpy into a single value, and it is the amount of energy in a system that is available to do work. And then, of course, we have a spontaneous reaction, which is a process that will occur without the need of additional energy from an external force. Next up, we have entropy and microstates. And here we're just going to touch on their correlation one with the other. But firstly, we should define what a microstate is, and as defined by the Pearson textbook, a microstate is a specific microscopic configuration describing how the particles of a system are distributed among the available energy levels. So in a mole of a substance, for example, not all of the particles are going to be in the same state, and so this dispersion of energy or different states is what we call the different microstates of a system. So here on the left is the Austrian physicist Maxwell Boltzmann, and he created this equation that we see here that calculates the entropy of a system by multiplying his constant, Boltzmann's constant, by the number of microstates, or by the ln of the number of microstates. And here you can see that as the number of microstates augments, so does the entropy of a system. And so there you can see the correlation. The more microstates are, the greater the entropy of that system. And this leads us to our second law of thermodynamics that states that all spontaneous processes produce an increase in the entropy of the universe. Gibbs free energy. So how are we going to determine if a reaction is spontaneous? So the sign of the enthalpy or the entropy is not actually enough to know whether a reaction will be spontaneous. And so that's why we use this equation right here, which calculates the change in Gibbs free energy. And we calculate this by having the change in enthalpy subtracted by temperature times the change in entropy. And if that value is negative, then we know that the reaction will be spontaneous. If that value is positive, we know the reaction will be non-spontaneous. And this equation is valid under these two conditions, at constant temperature or at constant pressure. But what about temperature? So temperature is obviously a very significant part of calculating your Gibbs free energy. And if you know the sign of your entropy and your enthalpy, then that can change depending on the temperature, even if those are set. So we're just going to look at this chart here that has it nicely laid out. So first, when we're looking at our enthalpy, if we have a positive enthalpy with a negative entropy, the reaction has the potential to be either spontaneous or non-spontaneous depending on the temperature. So it won't be spontaneous at low temperatures, but it will be at high temperatures. If we have a negative enthalpy and a negative entropy, again, we have the same possibility, but just inverted from the first one. So it will be spontaneous at low temperatures, and it will not be at high temperatures. If we have a negative enthalpy and a positive entropy, then our reaction will be spontaneous at all temperatures, both low and high. And if we have a positive enthalpy and a negative entropy, then our reaction will be non-spontaneous at all times. So it will never be spontaneous no matter the temperature. Okay, so now we're going to go over some practice examples just to reinforce everything that we went through or we just reviewed, and we're going to keep this equation here in mind in order to determine whether this reaction will be spontaneous or not. So with the first one, we're going to determine the temperature conditions in which 2NH4NO3 converted to 2N2 gas plus H2O plus O2 gas would occur spontaneously. So here we are given the enthalpy, and it should be noted that the enthalpy is negative, so this is going to be an exothermic reaction. Additionally, here we can see an increase in gas products
and this correlates with an increase in microstates. So this reaction is going to have a positive change in entropy. And so with a negative enthalpy and a positive entropy, we know that this reaction will be spontaneous at all temperatures. Okay, moving on to our next example, we're going to find the change in Gibbs free energy. For this equation right here, we are given the enthalpy as well as the entropy, and the temperature that this reaction is going to occur at is 298.15 Kelvin. So noting that the enthalpy is negative and so is the entropy, we know that this reaction is going to be spontaneous at low temperatures and not spontaneous at higher temperatures. So in order to find the change in Gibbs free energy, we're just going to plug these values right into the equation, and keeping in mind that the entropy has to be changed into kilojoules, as that is the unit measure for Gibbs free energy. And so just plugging this in, we get a value of negative 1,484 kilojoules. And so because it is negative, we note that this reaction will be spontaneous at this particular temperature, which is 298.15 Kelvin. Okay, and because we see that this reaction has the potential to be both spontaneous and non-spontaneous but at different temperatures, we're going to find the temperature of inversion. So we do this simply just by setting the Gibbs free energy change to 0 and then isolating to find the K value, so the temperature. When the Gibbs free energy is 0, that is when the system is at equilibrium. So we're going to set Gibbs free energy to 0. We're going to take the same values that we used in the first case to find the change in Gibbs free energy. So here we have negative 1,648 kilojoules for the enthalpy. The same value for the entropy, still converting it to kilojoules, but now the Kelvin is unknown, or sorry, the temperature, and so that's why we have just a K value there. So we're going to isolate by moving the enthalpy to the other side. It's going to become positive, and then we're going to divide through each side by our entropy here. And so with that, we get a final value of 3,000 for K, and so we know that at 3,000 Kelvin, at 3,000 degrees Kelvin, this reaction will no longer be spontaneous, and at any temperature above this, it will become a non-spontaneous process.
Moving on to some real-world applications. Like so many different parts of chemistry, thermodynamics are involved in our everyday lives, whether we notice them or not. But some simple examples that we probably see on our everyday, water freezes spontaneously below 0 degrees Celsius, and our sugar dissolves spontaneously. But some other uses that might not be so obvious or simple are in motorized vehicles. So all kinds of vehicles work on the basis of the second law of thermodynamics. So any motorized vehicle, so that can be cars, motorcycles, or airplanes. And thermodynamics is also present in medicine, which is really interesting. So cells are also considered to be thermodynamic systems. And this new branch of medicine, bioengineering thermodynamics, has helped there be a lot of new developments in medicine with a lot of new different approaches. But all living things waste energy in heat, and cells are spontaneously exchanging heat at all times. And so here you can just see simply in this diagram that the cellular work of a cell releases heat, and that increases entropy. Okay, and that brings us to the end of this presentation. Thanks so much for watching. Here are some links for more information. If you want to learn more about entropy, enthalpy, or anything like that, here you go, or as well as clarification, as well as the references that I used to put together this presentation. Thanks so much.